Okay, so now that we've had a little background here on energy, and we've at least mentioned heat, and the term temperature came up in the last lecture video, let's work a little further along and try to understand temperature and how it's important to chemistry and why it matters so much. Alright, so there it is, the term temperature, section 2.2. It's a term that gets thrown around a lot. It's unfortunately fairly misunderstood. It's not the same as heat. It's a measure of average kinetic energy, and so we'll try to distinguish it from heat and keep you aware as to why it's so important for our understanding of chemistry and chemical reactions. Alright, so we have at least 3 temperature scales that we should be familiar with, and in science, in particular the health sciences, temperature is measured in Celsius units, degrees Celsius. In chemistry and physics, we should really be using Kelvin because that's the absolute scale. And none of the sciences use Fahrenheit, which is the typical United States unit that's a hangover from what we call the English system. So if we look at these different temperature scales and we see the differences, the reference points for, say, boiling and freezing points of water, these are important things. So for Fahrenheit, 212 degrees Fahrenheit is the boiling point of water. It doesn't seem to be anything particularly special there. Celsius is it's set at 100 degrees Celsius, which is a good even number, right? 212 is an even number, but it's not that normal. And then finally, Kelvin is 373 Kelvin, and that has to do with the fact that Kelvin is an absolute scale. And so starting at absolute zero and working your way up is why Kelvin ends at such an odd number. If we look at the freezing points of water, we've got 0 degrees Celsius, which makes sense. Again, 32 degrees Fahrenheit. Fahrenheit is really based on the freezing point of a saltwater solution, which is why it's not 0 there. And then 273 Kelvin. So you notice both the Kelvin and the Celsius temperature scales have 100 unit differences between the freezing point and the boiling point of water. Whereas for Fahrenheit it happens to be 180 degrees, nothing particularly special there. But that's why we prefer Kelvin, because it is an absolute scale, and whenever we work with gases we have to make sure we're dealing with temperatures in Kelvin. But for much of the other work we'll do in the course, and certainly those of you headed into the health professions, Celsius will be pretty standard. Fahrenheit, unfortunately in the US, you're still going to see it quite regularly. So since we're talking health sciences, let's look at the other point that's compared across the 3 temperature scales provided: normal human body temperature. So Fahrenheit, 98.6 degrees Fahrenheit, and that's the one that your patients are probably aware of, and maybe the one you're most familiar with, but hopefully we'll continue to move in towards Celsius, and that 37 degrees Celsius will be more and more important. Certainly don't want 98 degrees Celsius for human body temperature, nor 37 degrees Fahrenheit. So just make sure you keep your temperature scale straight. And then for Kelvin, it's about 310 Kelvin units, although that one is pretty unlikely to make its way into the health sciences. So hopefully you have a better understanding of these 3 different temperature scales that are commonly in use, and why, although the Fahrenheit's the most common in the US, why Celsius and Kelvin really are much better units. Table 2.2 from your text just shows a comparison of other temperatures. So again, things that might be relevant, we say room temperature, which we say is 70 degrees Fahrenheit. Well, 21 Celsius is a normal room temperature. Again, being careful not to confuse it with 21 Fahrenheit, which is room temperature in my house in the winter because I won't pay for heat. Kelvin, of course, being somewhat strange, the numbers, until you get used to that scale. Absolute zero, where Kelvin is 0, or actually technically negative 0.2-ish, since absolute zero is a little off from where we first expected it. We've never achieved it, so it's sort of theoretical anyway. But again, that's where Kelvin is 0, and where Celsius and Fahrenheit both are lacking with their negative 273 and negative 459 respectively. Okay, so let's pause for a learning check, see how you're doing on relating these 3 different temperature scales by answering these 3 multiple choice questions. Number 1, what is the temperature of freezing water? Is it A, 0 degrees Fahrenheit, B, 0 degrees Celsius, or C, 0 Kelvin? Notice I didn't say degrees. Kelvin is not degrees, it's just Kelvin units. Number 2, what is the temperature of boiling water? Is it A, 100 degrees Fahrenheit, B, 32 degrees Fahrenheit, or C, 373 Kelvin? And finally, number 3, how many Celsius units are between the boiling and freezing points of water? Is it A, 100, B, 180, or C, 273? So hopefully you've already made your selections there. If you need another moment, just pause the lecture video and we'll see how you did. Alright, so hopefully you made the correct selections. For number 1, it's B, 0 degrees Celsius. That's the freezing point of water. In the other temperature scales, it's not 0, it's only the Celsius one that had that. For the temperature of boiling water, 373 Kelvin was the best answer. The other temperature scales were both in Fahrenheit, and neither one was the 212 Fahrenheit that corresponds to the boiling point of water in that scale, or that temperature scale. So the last one, whether I had asked Celsius or Kelvin here, same number of units, 100 units difference between the boiling and the freezing point, and that 180 may have distracted you there. That answer choice was the difference in the Fahrenheit temperature scale. So again, a lot of this is memorization, and I'm not really that into memorizing things myself. I prefer that you understand concepts. So if you're struggling here, it's not such a big deal. I just want you to get more used to these different temperature scales, especially Kelvin and Celsius, that you've probably seen much less frequently than the Fahrenheit scale. Okay, you probably won't always have 3 different thermometers on you to be able to tell the different values for a given temperature across the 3 temperature scales that are commonly in use. So here's a formula to convert between Celsius and Fahrenheit temperature scales. So on the Fahrenheit scale, since there's a 180 degree Fahrenheit difference between freezing points and boiling points of water, whereas on the Celsius scale there's only 100 degree difference, that's going to give rise to a different value, right? It's about 1.8 degrees Fahrenheit for every 1 degree Celsius. Not a nice, easy conversion, but one that we can do if we have to. I would provide the formula for you, and so we also have to account for the fact that there's a given temperature in either Fahrenheit or Celsius that we're trying to convert between. So the way we do that is by taking, to find the temperature in Fahrenheit, for instance, we would take 9/5 or 1.8 times the temperature in Celsius plus 32, again, to account for that fact that at 32 Fahrenheit we're at 0 Celsius. We could rearrange the formula to find a temperature in Celsius if we're given the temperature in Fahrenheit. So just be aware that we can do it either way, and mathematically, hopefully it's not too difficult for you to do that. You take the Fahrenheit temperature minus 32 and then multiply that by 5/9, the inverse, to get the Celsius temperature. Okay, so I would provide one form of the formula. You may have to manipulate it like I just did, but you should be able to convert easily between Celsius and Fahrenheit. And here we see that rearrangement more explicitly shown for you. So to find the Celsius temperature, if you're given the Fahrenheit temperature, we did exactly what I said. We subtract the 32 from both sides. We divide both sides by 1.8. And there we end up with a rearranged formula where the temperature in Celsius equals the Fahrenheit temperature minus 32, and then the result of that subtraction divided by 1.8. And both the 1.8 and the 32 are exact numbers, so they do not affect significant figures. Okay, so it's really going to be based on what the temperature in Fahrenheit or Celsius is to start, is going to be the same number of significant figures as your conversion answer in the other scale. Alright, back to that Kelvin scale, the one that as a chemist I prefer the most. Physicists and chemists have long been championing the Kelvin scale, but the physicists are much better at being consistent about it. Chemists, we often slip into degrees Celsius when we're not dealing with gases, but we do at least follow the rule of Kelvin temperature with gas laws, as you'll see when we get to that chapter. So the coldest temperature possible is negative 273.15 degrees Celsius, which is technically negative 0.15 Kelvin, although we should really readjust the scale so that it's absolutely an absolute scale. Theoretically, at that temperature, all motion stops. We mentioned in the previous chapter that temperature is a measure of average kinetic energy, the movement of molecules. So if there's 0 for the Kelvin temperature, then there really should be no molecular movement. And that's why we haven't been able to achieve that. We haven't been able to isolate a system enough to prevent all molecular vibration and really achieve absolute zero. We've come very close, within tenths of degrees, but it's still eluded us to achieve absolute zero, and some people think it's practically impossible to get to, although theoretically possible. So the Kelvin scale is based on an absolute zero, but it is also based on the units of the Celsius scale, where there's that 100-unit difference between boiling point of water and freezing point of water. So therefore, 1 degree Celsius is the same magnitude as 1 Kelvin unit. Of course, they're different temperatures because of that offset, but the conversion here between Kelvin and Celsius is much simpler than between Fahrenheit and Celsius, because the offset is really just that 273, or to be technical, 273.15. So if you are given the temperature in degrees Celsius and you want the temperature in Kelvin, you have to add 273 to that Celsius value. If you wanted it reversed, you would go ahead and take the Kelvin temperature minus 273, and you would get the Celsius temperature. And typically, if you wanted to go from Fahrenheit to Kelvin, you'd first go Fahrenheit to Celsius and then Celsius to Kelvin. Tends to be the easiest, and I would provide you with this one form of that temperature in Kelvin equals temperature in Celsius plus 273, just like I would provide the Celsius to Fahrenheit conversion formula. So here we see the table 2.2 again, and hopefully now you can look at least the Celsius and Kelvin values and see that they're all offset, where the Kelvin temperature is always 273 degrees, well, Kelvin units, right? Not degrees for Kelvin, but Kelvin units above the Celsius temperature. So just reiterating that. And we see absolute zero is 0, but we haven't achieved it. Helium boils at 4 Kelvin, so very cold to get liquid helium. It's a gas from 4 Kelvin on up, but liquid helium is used typically, if we're thinking about the medical setting. Magnetic resonance imaging will often have liquid helium to cool the magnets to achieve this magnetic field strength you need to get a good quality image, and therefore liquid helium is important, but it is very cold, and we've got to replace it from time to time because it'll all boil off, since it's tough to keep anything at that low a temperature. All right, here we see that Kelvin, Celsius, Fahrenheit image again, a little larger this time. And again, just drawing your eye to it so that you take a pause, a step back, and just appreciate those differences and get more familiar with the Celsius and the Kelvin scales, because you're probably quite familiar with Fahrenheit from the common use in the United States. All right, so thinking again, the health sciences, I know a number of you are interested in the health sciences, and that's why we do try to have links there. So oral body temperatures vary. Normal is 37.0 degrees Celsius, or again 98.6 degrees Fahrenheit. But temperatures, lower temperatures are common in the morning. The body, after rest in the evening, is typically at a lower temperature compared with after exercise or just after daily activity, and goes up to about 37.2 between 6 and 10 p.m. And then temperatures, of course, can go above that 37.2. That's an indication of fever, and if it climbs too high, there's hyperthermia, and then if that's not addressed, ultimately death if the temperature is too high for too long. Likewise, if your body temperature drops too much for too long, we go first to hypothermia and then ultimately to death as well. So it's very important that we keep that body temperature within that normal range of, say, 36 to 38 degrees Celsius, or 96.8 to, say, 100.4 degree Fahrenheit. Otherwise, if we're outside the normal range for any length of time, again, aside from a mild fever for the duration of a cold, then if you're much above that, if you're at a high fever or even beyond that, or at your other extreme at the low end with hypothermia, you're not going to make it if you stay there too long. It's not good for the proteins and enzymes that we have. They function ideally within that normal range, and they don't do well above or below it. Okay, so looking back at our problem-solving strategy, let's modify it slightly for solving a temperature problem. So our guide to calculating temperature, first we're going to state the given and needed quantities like we always have. And now we're going to write a temperature equation if we're going to be converting between temperature scales. And then finally substitute in the known values and calculate the new temperature. So let's apply that strategy to this problem. We have a person with hypothermia having a body temperature of 34.8 degrees Celsius. What is that temperature in degrees Fahrenheit? So applying our steps, we have step 1, state the given and needed quantities and analyze the problem. So we're given 34.8 degrees Celsius. We need to know what that temperature relates to in degrees Fahrenheit. Step 2, looking at our temperature equation, well, we want temperature in Fahrenheit. And we're given temperature in Celsius, so the ideal equation to use is temperature in Fahrenheit equals 1.8 times the temperature in Celsius plus 32. Okay, make sure you do the 1.8 times the TC before you add the 32. The order does matter there. Okay, so finally substituting in the known values and calculating that new temperature, we have 1.8, which is an exact number. It's not subject to sig fig rules. Multiply that by the 34.8 degrees Celsius, which has 3 sig figs, and then we add 32 to that result, which is an exact number, doesn't affect sig figs. So we get 62.6 is the result of multiplying 1.8 times 34.8. Plus 32 to get a final answer, also in the tens place, also with 3 sig figs, 94.6 degrees Fahrenheit. So hopefully you were able to solve that correctly and to apply the sig fig rules correctly. But again, if that gave you trouble and you're trying some additional problems, make sure to check with me if I can be of assistance. And we'll also have another learning check right now to make sure if you did get this one that you're able to continue to perform well on this topic. Okay, so here we go, another learning check. This time we have a pepperoni pizza is baked at 455 degrees Fahrenheit. What temperature is needed on the Celsius scale? So hopefully you've already gotten the hang of the Celsius scale. Fortunately, these answer choices, A, 423 degrees Celsius, B, 235 degrees Celsius, and C, 221 degrees Celsius, they're all less than the Fahrenheit temperature. We know that Celsius should always be less than Fahrenheit. So now it's just a matter of figuring out which one is the best answer, and that would rely on you solving the same sort of problem that we just worked together. So it's another chance to practice and make sure that it's going well, or find out if you're still struggling. All right, so here we have the given 455 degrees Fahrenheit. What we're looking for is that temperature relationship in the degrees Celsius value. So the formula that we're looking at here is Tc equals Tf minus 32, and then the result of that subtraction divided by 1.8. So we've rearranged the formula so that we can solve for temperature in Celsius, whereas last time we solved for temperature in Fahrenheit when we were given Celsius. Okay, and after we substitute in the known values and calculate that new temperature, we find the answer to be 235 degrees Celsius, which was answer choice B. So hopefully that was not too difficult. And again, all the answer choices were given to the ones place, so you didn't have to worry so much. But again, it's important we always consider sig figs, and so our answer should be to the ones place. All right, if that's working well for you, then great. If you're struggling, try some additional problems. If it's still not going well, please reach out. Let me know if there's something I can do to help you. All right, let's try another one of these, and this time we're going to deal with that negative that oftentimes appears in the Celsius and Fahrenheit scales. Obviously, negative would be unusual in the absolute Kelvin scale. So on a cold winter day, the temperature is negative 15 degrees Celsius. What is that temperature in degrees Fahrenheit? Is it A, 19 degrees Fahrenheit, B, 59 degrees Fahrenheit, or C, 5 degrees Fahrenheit? And if you've been in the U.S. for any length of time, especially if you've been in the Binghamton area or any place in the Northeast or Midwest in wintertime, you probably know right now to toss B out. That's not a winter temperature, not a cold winter day anyway, for those of us who've been through some winters in the Northeast. So now it's really a matter of figuring out between A and C which is the correct value. So please pause the lecture video if you need to figure that out. Otherwise, if you've already solved it, let's see how you did. Alright, just like we've been doing, we'll apply our steps. So step 1, we'll state the given and needed quantities to analyze the problem. So we're given minus 15 degrees Celsius, and we're looking for the temperature in degrees Fahrenheit. So write that temperature equation, the form that we used before, where we're solving for temperature in Fahrenheit. It equals 1.8 times the Celsius temperature, and then after we get that product, we add 32. Alright, so in step 3, we're substituting in that value, the minus 15, and we see that the final temperature, the product at least of the 1.8 times the minus 15 gives us a minus 27. When we add 32 to that, we get a positive 5. And because of the addition subtraction rules at the end, we're taking it to the ones place. We're not doing the multiplication division rules, even though that is a part of it. We're finally adding at the end, and so we're doing the addition subtraction rules. So we end up with the ones place, just like the minus 15 degrees Celsius was to the ones place. So 5 degrees F, answer choice C is our best answer. And we just note there at the bottom, use the change sign key on a calculator to enter the negative sign. So there should be a plus or minus sign that allows you to enter that result if you aren't able to put it in as a minus 15. If you're having trouble with your calculator, of course, let me know. You could even send me a picture of the calculator you're using, and I could help let you know which key on that calculator would help you to get the negative sign. Okay, so let's end this lecture video with one last learning check. And this should be an easy one, I hope, because it's only going to involve addition or subtraction, since we're going here between Kelvin and Celsius units. So what is normal body temperature of 37 degrees Celsius in Kelvin? So our answer choices are A, 236 Kelvin, B, 310 Kelvin, and C, 342 Kelvin. I would provide the relationship that Kelvin equals temperature in Celsius plus 273, and that's actually the form that you need right now, but you would have to rearrange it. If I were giving you Kelvin and asking for Celsius, then you'd have to rearrange that formula. Hopefully that's pretty simple. Okay, so go ahead and pause the video if you haven't solved the question yet, and then start back up as soon as you solve, and we'll see how you did. Okay, so there it is, step 1, state the given and needed quantities, analyze the problem. So we're given 37 degrees Celsius. What we're looking for is the temperature that relates to in the Kelvin scale. And so step 2 is writing the equation. It's just as I would give it, Kelvin temperature equals temperature in Celsius plus 273. Okay, and finally, step 3, substitute it in the known values and calculate the new temperature. So we have the Kelvin temperature is going to equal the Celsius temperature, 37 here, plus 273, which gives an answer of 310 Kelvin, which was answer choice B. If we wanted to indicate that the answer is to the ones place, which is what we should, since the Celsius temperature was to the ones place, we really should put a decimal point there. I didn't show it here on the slide, but it is important to indicate if you really want to drive home the message that 310, that ones place, is significant. Alright, so hopefully that was a pretty simple one, and hopefully all of them have been fairly simple for you. You're catching on. This temperature scale business isn't going to hold you back. If you're struggling with it, please continue to try and reach out for help, because it is important, especially as we do more problem solving, in particular when we do gas law problems, and using that Kelvin scale is going to be very important. So please stick with it if you're having trouble. All right, hope to have you with me for the next subtopic.